Hi, everyone. Well, we're just going to go ahead and continue on with experiment number 7. Going to work on the first law today, but before we do that, just note something. I really don't know where I'm at. Somewhere I'm in here. I suppose you might be feeling the same way. I have no clue where I am, except here in my house. Just before we get going, just a couple of things before I actually start the lecture on the experiment. I know that this is kind of hard being at home all the time. I know I'm a extrovert. Like being with people, and being home by myself is not an easy thing. And so maybe just give you a sense of how I'm handling it and what I'm doing. My goal is to try to serve everyone and be there for you. I'm taking care of family members who are in need, and I'm taking care of my home and cleaning and taking care of upkeep, making certain I exercise, make certain that I come out of this feeling like I've done the best I could possibly do. And I think that right now that's what you should really work toward, is to come out of this time and say, you know what, I did exactly everything that I should have done in this time. I worked hard on my schooling. I helped around the home. I took care of myself. I maintained a regimen so that every day I made my bed, I cleaned myself up, I took care of whatever needed to be taken care of. If you're with people that can grind on your nerves a little bit, that happens. Doesn't mean anything big time. All it means is sometimes you might need to get off into another room by yourself for a little bit and just relax and breathe and take it easy. If you're not sleeping well, remember that there's some things that you can do. Slow motion exercise before bed, breathing, meditation, relaxing. These are some of the things you can do right before bedtime to maintain equilibrium and getting good rest. Remember, good rest will help and give you good health. So, good rest means good health. So, take care of these things. So, let's see, I've got the lab book right here, and I'm looking at this. We've finished page 84. We've done some of the definitions, A through E and H. I'll give some more in just probably today. We went ahead and drew the major and minor axes, and we made certain that the major axis passed through the origin, which is where one of the foci is, and we made certain that this side looks like that side, so it's not somehow skewed to one direction somehow. We measure the distance from the edge of the orbit over along the major axis to the foci, and made the same distance to locate the second focus right there. And so now what we're ready to do is to continue actually beginning to work on the 3 laws of Kepler, and showing that this orbit do they do this does, that is, actually show that the 3 laws work for this satellite moving around the sun or orbiting the sun. Let's see, we finished page 87. I gave you the moon's radius last time. You're supposed to calculate the moon's diameter by simply multiplying the radius by 2. We answered the question at the top of 88, so make certain that's done. And now you should have finished the table 2 on the bottom of page 88, and go back to the previous lecturette, number 7.3, to verify how to do that. Again, I'm watching for emails and also comments on my Facebook group for you guys. Remember what it is. It's Prof. Astro Mike, CC Astronomy. Please join if you have not, and you're going to post questions there. Now, what we're going to go ahead and do is try to answer the things about eccentricity that's on page 89, going into page 88. And then finally on page 91, we can answer and find out the way to deal with Kepler's first law. So let me just finish up this, and so we can finish page 89 and 90. Eccentricity is just a mathematical term that refers to how squashed or how much away from a circle an ellipse is. Remember, an ellipse can be very drawn out or it can be very circular. And what we said is that the eccentricity E, which has been mentioned on a previous lecturette, is the length between the two foci, which we call 2D, divided by the length of the major axis. Which we said was 2A. And what we said is that for an ellipse, it basically ranges from 0 to 1, but does not include that. So where is it that there is an eccentricity of 0 or 1? And what we said is that there are different shapes we find in mathematics and in nature. So this is the shape, and this is the eccentricity. And so let me make a little table here. For a circle, here's a circle, here's the center of the circle, here's the diameter, the eccentricity equal to 0. And then we have the ellipse. So here is the ellipse with the two foci and the major axis. And we said that it falls between 0 and 1. That means the eccentricity is more than 0, but less than 1. The next shape is the parabola. And so if this is the xy axis, parabola looks kind of like this, and the eccentricity of a parabola is 1. Then we have another shape that's known as a hyperbola. And I'm going to make very simple, not totally all the information about the hyperbolas. It looks kind of like a squid, a more open parabola. It turns out that its eccentricity is more than 1. And as that opens up more and more and more, getting closer and closer to a straight line, the greater the eccentricity. So let me leave that there for a moment so you can see it. And of course, you can stop this. If we look at this, if I look at these two ellipses, then I know that this eccentricity must be closer to 0 than 1. Because look at again, the eccentricity of a circle is 0. And that's very close to the circle. Whereas this eccentricity must be getting closer to 1 simply because it's getting more and more squished open until finally it would just break open if it got any more squished than what it is there. And so if we go back to the book, first off, the top of page 89, the eccentricity basically just gives how far away from a circular shape the ellipse might be. And we'll only worry about ellipses on that particular question. Now, you have a length of given in table 2 for the distance between the foci. You also have the length of the major axis there. So on the middle of page 89, please calculate the value of the eccentricity for the ellipse of the satellite that you're playing with that orbited the moon. And notice this, it is the length divided by a length. And what that means is if the units of length are meters, then you're going to have meter divided by meter, which means that basically those units from the top, from the numerator and the denominator of the equation for eccentricity will cancel. So eccentricity is a unitless number. Don't have a unit with this. Next thing is that the length between the foci is smaller than the length of the major axis. Therefore, let's say it's 1 and for the top and 2 for the bottom, be 1/2, so it'd be less than 1, so you expect that. Okay? So, again, on the bottom of page 89 is just what we said here, and the top of page 90 is, again, finishing up on parabolas and hyperbolas. And I would just say, go back to the previous lecturette to try to answer the question on the top of page 90. And then refer to this lecturette for the second question there. Go back and just do the best you can with that. If you have questions, let me know. And again, look at what we have here and what I talked about up there to answer those problems 1, 2, and 3 at the bottom of page 90. Let me know if there's any questions. Take your time. If you have to, go back over the lectures, and let's just make certain that you are prepared. So now, finally, we are able to actually start talking about the laws that Kepler came up with for how things orbit. Now, they're called the 3 laws of planetary motion, but really it's more accurately the 3 laws of orbital motion, regardless of what is actually doing the orbiting. In this case, it's a satellite around the moon. They also hold for the moon around the Earth, or the Earth around the sun. These laws are general, and we use them all the time. So I'm going to do this law, Kepler's first law, and then what we're going to do is I'll explain how the law is done, what you fill out on page 91, and then I'll explain what is meant by percent difference, which is what you have to calculate. So let's remove this particular graph. Oh, excuse me, I guess I did. Let me go ahead and just remove this stuff right here. And let's go ahead and let me show you how to proceed with Kepler's law, the very first law. So we use if I can get that to detangle. So let me put this up here and I'll write down the law. Very good tape. Okay. So the first law basically says this. You can read it on the top of page 91. It says planets, in this case will be the satellite, because remember it's more general, orbit in elliptical orbits with the sun, in this case the moon, the sun centered on a focus. So that's the kind of the general way it's spoken of, and you can see it a little bit better written on the top of page 91. Planets move in elliptical orbits with the sun centered on a focus. Well, in this case, since we're talking about the orbit of a satellite around the moon, the way that we use it here is that a satellite moves in elliptical orbit with the moon centered on a focus. And so again, I'll say it. This satellite moves in an elliptical orbit around the moon, and where the moon is located at is centered on a focus, which is right here. So let's make certain I label this a little bit more carefully. Get a pen here, or a pencil. There's a focus right here, and here's a focus right there. So we have the focus. Now, there is a rule that you find when you study ellipses, that there is one way to tell if a shape is an ellipse or not. First off, the shape has to have two foci, a focus there and a focus there. Remember, the distance from the edge out to the focus is equal to the distance from that edge out to the focus. They're symmetric. And what the rule is, if I choose any point, so I chose a point I called A here, it's just any point I want to take. There's no particular place, so I just chose there. And then I chose the second point over here. Again, just arbitrary. I chose it. I wanted them to be far apart, so I don't mix up the graph. And the rule says this, that if I draw a line from this focus to the point, and from the point to the second focus, so I have two lines to that point. Then I do the same thing for the second point. I draw a line from the focus at the moon out to the point, and from the point to the second focus, that if I measure the length of this line and I add it to the length of that line, so I get a sum for that point A, and I do the same thing for point B. I take the length of this line and I add it to the length of that line, so I get a sum for point B, that those sums will equal. So what I'm saying is that if I use what I call here the length of the first line plus the length of the second line for point A, that it will equal the length of the first line for point B plus the length of the line for point B. They'll equal. And that's what you have to do here. So if I look at the book on page 91, you have the first law of lengths. So this could be 1, 2, 3, 4. And so that's on table 3. Find the two lengths for each point, and then sum those lengths for each point, and that's what's listed on point 4, on table 4, Then what we're going to do is compare just how good they are by using something called the percent difference. So let me explain what is going on here. What we want to do is to verify if this is true, that those two lines for point A, if I add their lengths, is equal to the two lines for point B and reasonably close. And if so, then that says that that shape of the orbit is an ellipse. Now it looks like an ellipse, but we want to prove it because that's how we do things in science. We prove it, we just don't assume it. Because again, science is not opinion. It is based on measurement. Our ideas then are based on predictions to verify that our ideas are right. And we don't ever just assume that we understand everything. We have to test it. So what are you going to do? You choose 2 points, A and B, and they can be anywhere along. I would suggest having them separate on other sides of the from one another. Draw a line from this focus to the point, and from that point to the other focus. Measure the length of both lines. List that in table 3. Do the same thing for point B. Draw the line from the focus at the moon to the point B, and from the point B to the second focus, measure their lengths, and then list that again in table 3. Then add those two lengths up for B and add those two lengths up for A and put those sums in table 4. That's all the measurements you have to make. And then what you're going to calculate is something called percent difference. Percent difference means this. What is it about? So let's think about what we just have done. We've measured two sums. And so we have two sums, and we have therefore two experimental results. And we want to compare those two experimental results together. And so the way we do that is the percent difference. Now, if you look on the top of page 92, what you find here is the equation. So you have two sums. We'll call it measurement 1 and measurement 2. And so you have the two sums of table 4. And so the percent difference is just defined to be the difference of the two sums, and we take the absolute value of that. In other words, we just want to strip off any minus signs that or negative signs that might crop up in that subtraction. So percent difference is always a positive value. I'll say it again. Percent difference is always a positive value. Take the difference of the two sums on table 4. If there happens to be a negative sign, just strip off the negative sign. And then what we do is we divide that by the average of the two sums. How do you average two numbers? You add them together and you divide it by 2. So you divide this by the sum of the two measurements and divide that sum by 2, and then you multiply it by 100. And that will be your percent difference, and you see that. Now, I don't expect that your sums will be the same. First off, they're based upon our drawings, and they could have problems with them. They're based upon our measurement. There could be problems with that, and they're based on the data, and there could be problems with that. Maybe there's some issues with the data. So if your two sums are not exactly right, does not mean that you're wrong. Now, what we want to see is that this sum, that this percent difference is not very big, meaning less than 10%. What that means is that if, say that you got a percent difference of 5% when you calculate this right here using the two measurements of the sums. Say it's 5%. What that means is that your two sums of those lengths are within 95% of one another, which indicates probably they're the same. It's just that there's error in measurements. And that's what you report. And then what you do, frankly, after that is simply go ahead and make a comment from that question on the top of page 92. Now, first off, you calculate your percent difference. You write down what your percent difference is. It should be a positive number on the top of page 92, and just put percent there with that number. And then the question says, is it exactly 0%? And more than likely it's not. And again, the reason why is there's errors in drawings and errors in measurements and error perhaps in data. So it's not surprising. If it's not, then if it's 5–10%, that implies that more than likely those two sums are the same, which says then that this satellite is moving in an elliptical orbit, and that's what I would expect it to be. If you're getting a percent difference of 50% or something, then you more than likely have done something wrong. In which case, go back and look at the lecturettes, and if you're still having troubles, then let's talk via email or the Facebook site, and I'll see if we can work out what you've done. One thing that would be helpful is if you're having big problems, take a picture and send that in the email so that I can see what you've drawn and try to get some sense of what's happening. I hope that this is making sense to you. So where do we go from this? Well, what we have to do is we have to then go ahead and go to the second law. The second law is, frankly, there's no other way around it but to say kind of annoying, because you have to do a lot of counting of little squares and partial squares, and I will explain that in the next lecturette. This is lecturette number 7.4. I will come up with lecturette number 7.5 today and send them off. I would say we probably have, counting the next one, 2 or 3 more lecturettes for this lab, and then I will be finished. It will be due a week from this Wednesday, and I'll give you a date as we get toward the end so that you know exactly what day this is due. And so let me know if you're having troubles. I'm here. I'm watching for emails. I'm watching for comments on Facebook. We will continue working this out. Don't be afraid of this stuff. You can do it. And together we will work and try to make certain that you do a good job. Guys, take care of yourselves. I hope that you know that you're cared about, that I will watch out for you. We will work on this, and I will talk with you soon. Bye-bye.